Imagine building an internet network with no cables, no towers, and no fixed location, made entirely of thousands of satellites racing around the Earth at 17,000 miles an hour. Now imagine every single one of those satellites has an expiration date, burning up in the atmosphere after just a few years, which means you have to keep launching replacements constantly, forever, just to maintain the same service you had yesterday. Add the constant risk of collision with space debris, ground stations tracking every satellite in real time, and a launch schedule that never actually stops. This isn't a temporary project. This is what it actually takes to run a global satellite internet network, and the bill behind it never goes away. Most people think of a satellite constellation the way they think of a bridge or a power line, something you build once and it simply exists from then on, quietly working in the background. That assumption is completely wrong, and understanding why reveals one of the strangest business models ever created. A low Earth orbit satellite constellation isn't a single infrastructure project. It's a permanent, continuous manufacturing and launch operation that never gets to stop. Because the very orbit that makes the service fast and reliable is also the orbit that guarantees every satellite will eventually die and need to be replaced. Let's start with why these satellites are placed so low in the first place, because that decision is the root of almost every cost in this entire business. Traditional communication satellites sit in geostationary orbit, over 22,000 miles above the Earth, where they can remain fixed over a single point, and orbit only a handful of satellites are needed to cover an entire hemisphere. But signals traveling that distance introduce a noticeable delay, which makes activities like video calls or online gaming frustrating. Low Earth orbit constellations solve that problem by flying satellites at altitudes of just a few hundred miles, dramatically reducing signal delay. But that lower altitude comes with a brutal trade-off. At that height, there's still enough trace atmosphere to create drag, and that drag slowly pulls satellites downward over time until they eventually burn up on re-entry. A satellite in geostationary orbit can last decades. A satellite in this lower orbit typically only lasts around 5 years before it has to be deorbited and replaced. Now, do the math on what that actually means operationally. To provide continuous global coverage, a company needs thousands of active satellites in orbit at any given time. And because each one only lasts roughly 5 years, you're not building a network once. You're committing to manufacturing and launching a meaningful fraction of your entire constellation every single year, forever, just to maintain the exact same level of service you had the year before. This isn't a maintenance cost in the traditional sense. It's a permanent replacement treadmill that never slows down, and it fundamentally changes how you have to think about the economics of the entire operation. Let's talk about manufacturing, because building satellites at this scale required an entirely new approach to the industry. Traditional satellites, the kind built for geostationary orbit, are often custom-engineered, built one at a time over months or years, and can cost tens of millions of dollars each. That approach is completely incompatible with a constellation that needs thousands of satellites and has to replace a significant portion of them annually. So companies operating at this scale had to build dedicated satellite factories capable of mass production, essentially applying assembly line manufacturing techniques to spacecraft, something that had never really been attempted before at this volume. Even with that manufacturing efficiency, producing satellites by the thousands still requires enormous ongoing capital investment in specialized components, propulsion systems, solar panels, and communication equipment, all of which have to meet the reliability standards required to survive the harsh conditions of space, where a single component failure often can't be repaired at all. Now let's talk about launches, because getting thousands of satellites into orbit and continuing to launch replacements indefinitely is one of the largest recurring costs in this entire business. Even with reusable rocket technology dramatically lowering the cost per launch compared to previous decades, launching dozens of satellites at a time still costs millions of dollars per mission, and a constellation operator might need to conduct launches on a nearly weekly basis just to keep pace with both network expansion and the ongoing replacement of aging satellites. This isn't a cost that appears once during initial deployment and then disappears. It's baked permanently into the operational model, because the moment launches stop, the constellation begins to shrink as old satellites deorbit faster than new ones arrive to replace them. Let's talk about ground infrastructure, because a satellite constellation is completely useless without an enormous network of ground stations to actually connect it to the internet. These ground stations, often numbering in the hundreds, have to be built in strategic locations around the world, each one requiring land acquisition, specialized tracking antennas capable of following fast-moving satellites across the sky, high-capacity fiber connections to actual internet infrastructure, and continuous staffing to monitor performance and handle technical issues. Every single one of these ground stations represents an ongoing operational cost, electricity, maintenance, staffing, and connectivity fees that scales with the size of the network being supported. Here's a detail that surprises people. Because satellites in low orbit move so quickly relative to the ground, a single ground station can only communicate with a given satellite for a few minutes before it passes out of range and another satellite has to seamlessly take over the connection. This requires enormously sophisticated software constantly calculating which satellites are visible to which ground stations at any given moment, and orchestrating handoffs between satellites so smoothly that a user's internet connection never notices the switch. Building and maintaining that software infrastructure requires large teams of specialized engineers whose salaries represent yet another permanent operational cost layered on top of everything else. Let's talk about space debris, because this is one of the most underappreciated risks in the entire industry. As more satellites from more companies and countries get launched into low Earth orbit, the risk of collision between objects increases substantially. A single collision doesn't just destroy two satellites. It can create thousands of pieces of debris, each one moving at orbital velocity, capable of destroying any other satellite unlucky enough to cross its path. To manage this risk, constellation operators have to continuously track the position of their own satellites relative to other objects in orbit, and when a potential collision is detected, satellites have to perform evasive maneuvers, using their onboard propulsion systems to slightly adjust their orbit and avoid the collision entirely. Modern constellations perform these collision avoidance maneuvers routinely, sometimes thousands of times per year across the entire fleet, and each maneuver consumes propellant, a limited resource that, once exhausted, effectively ends that satellite's useful operational life, regardless of how much longer its other systems could have functioned. If you're finding these hidden operational realities as fascinating as we do, hit subscribe, because every week we break down what it actually costs to keep the world's most complex systems running, the numbers nobody puts in the headlines. Let's talk about regulatory and spectrum costs, because operating a global satellite network requires navigating an extraordinarily complex web of international agreements. Radio spectrum, the specific frequencies satellites use to communicate with the ground, is a limited and heavily regulated resource, and companies have to secure spectrum rights across potentially dozens of countries, each with its own regulatory body, its own approval process, and in many cases, its own fees. Beyond spectrum, operating in a given country's airspace to actually provide service often requires separate licensing agreements, and navigating that regulatory landscape across a truly global service area requires dedicated legal and government relations teams operating continuously, negotiating and renewing agreements that can take years to finalize in some jurisdictions. Let's put a full year together, because that's where the real financial scale becomes clear. Between the ongoing cost of manufacturing thousands of replacement satellites annually, launching them via a near-continuous rocket schedule, operating and maintaining hundreds of ground stations worldwide, funding the engineering teams required to manage orbital software and collision avoidance systems, and navigating international regulatory and spectrum licensing costs, the total annual operating expense for a major satellite constellation can run into the billions of dollars, and that figure doesn't include the substantial ongoing research and development required to design next-generation satellites with better capacity and lower per-unit costs. Here's the number that puts this business in perspective. Industry analysts estimate that the total investment required to build and sustain a competitive global satellite constellation, accounting for the permanent replacement cycle inherent to low Earth orbit, can exceed $10 billion before the network reaches a mature, self-sustaining subscriber base large enough to cover its own ongoing costs. And unlike almost any other infrastructure investment, this isn't a cost that eventually stops. There's no point at which the constellation is simply finished and paid for. The 5-year satellite lifespan guarantees the spending never actually ends, which means the entire business model depends on generating enough subscription revenue, month after month, year after year, to fund a launch and manufacturing operation that runs continuously and permanently, essentially forever. So why does anyone build a business with costs this relentless? Because the alternative, providing internet access to remote, rural, or otherwise underserved regions using traditional fiber or cellular infrastructure, is often even more expensive or physically impossible, given the terrain involved. A satellite constellation, despite its brutal ongoing cost structure, can provide connectivity to literally any point on the planet without laying a single mile of physical cable, which for certain markets, maritime shipping, aviation, remote scientific research stations, disaster response zones, and rural communities far from existing infrastructure, represents a service that simply cannot be replicated any other way. That unique value proposition is what allows companies to charge subscription prices high enough to eventually fund the endless replacement cycle running quietly overhead. So the next time you connect to a satellite internet service and the connection just works, remember what's actually happening above you. You're looking at the visible result of a permanent manufacturing operation producing satellites by the thousands, a near-continuous rocket launch schedule replacing aging spacecraft before they burn up in the atmosphere, hundreds of ground stations tracking fast-moving objects across the sky, and a fleet performing routine collision avoidance maneuvers to survive in an increasingly crowded orbital environment. None of it ever really finishes. The connection is instant. The operation behind it never sleeps. Disclaimer: this content is for educational and entertainment purposes only. Operational costs are estimates based on available data.